Hello, everyone. Today, I'm going to present our paper with the title of A Hardware-Based SoC Monitoring in Light Solution for Automotive Industry. It is a part of an Innovate UK funded project aimed to improve the safety and security of tomorrow's CAFs. The hardware solution is developed by Siemens, while Coventry University developed a testbed demonstrator representing a full-scale automotive functional architecture to assess and validate the proposed solution. My presentation is divided to four main parts. The first part is to give a picture of current automotive cybersecurity and available automotive hardware solutions. Then I will introduce the proposed Siemens SoC hardware monitoring solution, which is going to be used in future CAFs. The third section is about how to design and build a testbed employed to verify the automotive security solutions. And finally, to give some example of how this testbed is used to validate the Siemens SoC monitoring solution by running selected abuse cases. Let me start with this picture, which is probably familiar to many of you. Nowadays, it is common practice that each car is embedded with about 100 microcomputers called ECUs, which controlling and dealing with different functionalities of the car, ranging from powertrain to infotainment subsystems. They are also connected by in-vehicle networks, which is in cybersecurity terms, it provides for some attacks to happen. To make it even worse, today's cars are usually equipped with head units and telematics, which gives the ability to connect the car to the outside world through GPS, cellular, Wi-Fi system, and so on. These add even more attack vectors, which brings more vulnerabilities and consequently damages to the car and its passengers. Our studies actually focus on two of these network protocols. The main one is the CAN bus protocol, which is probably the oldest and the most used automotive network protocol and brings a number of vulnerabilities to the vehicle. First one is its ability to broadcast transmission all over the network, which means that any ECU can send message and receive message by all the other ECUs. Also, it doesn't have any authentication, which means that when you receive the message, you cannot validate if it actually arrived from another ECU inside the vehicle. It also doesn't support encryption, means that the exposed messages will be easily understood by the attackers. And finally, because it is ID-based priority scheme, which means that when two ECUs sending messages at the same time, it is going to be prioritized based on their ID. This means that if an ECU compromised, it can send messages over the network to prevent other ECUs to send messages by sending high priority messages. Also, nowadays, the application of SoCs are dramatically increased in modern cars and will be used in most of the modern future CAFs. However, the security of automotive system on chips or SoCs is not a straightforward subject, because SoCs are becoming more and more complex as they include many sophisticated applications such as hardware acceleration. And this makes those applications and the entire SoC security a great challenge for the automotive industry and also for the semiconductor industry, especially if their designers want to reduce the area cost and the power consumption. Therefore, it is essential to review and understand the SoC's AXI interconnect vulnerabilities which provide connection to a number of non-secure hardware inside the car. Also, connection to at least one type of network or services inside the car, which means it opens a gateway to the other network protocols inside the car. And also, it gives access to sensitive information, such as mobile banking details or private information stored on one of the systems. Also, as a reminder, AXI Interconnect was introduced by ARM in 2003 as the third generation of its AMBA bus protocol to provide good power efficiency, efficient and reliable data transfer between the SoC subsystems. Now I want to talk about 3 examples of automotive hackings. The first example was reported actually around 20 years ago, where a security expert were able to modify ECUs of a car. The performance of the car has been increased by identifying and isolating the proper ECU and reflash it to change the control of the engine. For instance, changing the amount of fuel fed to the engines to change the performance of the car. It clearly can compromise the integrity of the ECU. So if someone can change the control command of the ECU, so can also do it in a bad way and run it to a trouble. The next example is a well-known and more recent one performed by Miller and Walasek. They could compromise the head unit of a Cherokee Jeep wirelessly via mobile connection. This allows them to take control the car features and would also let them, for example, to disable the braking system. Imagine the scenario in a real world and how it can make damages to the safety critical features of the car, such as braking or suddenly increasing the speed of the car or other safety critical features. The same 2 researchers, after 2 years, published another case study on the same car. This time, they have physically connected the attack device to the car network to allow them send messages to the ECU of the cars directly. They put the ECU in the booting loop and which allows them to send malicious control command directly from attack device. This time they could have more control on the car features such as steering wheel, brakes, and again other safety critical features of the car. Modern automotive systems are becoming very complex beasts in their own right. These consist of clusters of ECUs, typically connected to one or more in-vehicle networks. Many of the individual ECUs are simple in nature, but others are not. Now I will give you an example of one of the current SoC system which is being used in automotive industry and called ADAS systems. They are used to control adaptive cruise control, driver monitoring, lane departure warning, and collision avoidance. These employ an array of cameras, LiDAR radar, and ultrasound sensors. In addition, they themselves contain sophisticated systems that process the data from the sensors and systems that control electromechanical actuators inside the vehicle to perform automated steering and braking. Therefore, it is critical to ensure the behavior of such a cluster of systems and subsystems, which should run with precise timing, can be kept in check. The diagram of such ADAS system is shown in this slide. So due to these challenges, we proposed a hardware-based SoC monitoring in live solution. In this slide, I provide a demonstrable SoC platform, which is integrated on a FPGA system. It is also capable of emulating collection of ECUs to run abuse cases. The FPGA itself has contained several Siemens monitoring IPs, also referred to as embedded analytic IPs, as well as a number of hard and soft CPUs. The analytics IPs are shown in the teal color. These IP modules are used along with analytics software to detect and mitigate a number of security threats. The implemented IP blocks are an analytic CPU available for configuring and analyzing data from the monitoring infrastructure, system CPUs, which are 2 RISC-V, 4 ARM A53, and 2 ARM R5 CPUs, available for executing system functions such as ECU emulation. CAN bus, which is actually a CAN transceiver in conjunction with the analytics CPU, is served as a prototype of a CAN bus Sentry. 3JPAN for providing ability to easily halt, resume, and reboot code on RISC-V cores. Static instrumentation for enabling software-based monitoring. Virtual console for enabling communication between code runnings on CPUs and debug cost. Direct memory access, DMA, for providing access to the entire address space. And also bus monitors, 8 of them, for providing observation of all AXI interfaces of interest. In relevant cybersecurity context, they also enable monitoring, detecting, and removing errors in interconnect transactions. Therefore, Siemens analytic IP introspection monitors, which you can see them in light green, used to assess how well the automotive SoCs, such as ADAS, are operating. These monitors are runtime configurable and provide rich data, which can be used by analysis tools to provide insight into the issues that may be observed. For example, the AXI bus monitors are protocol aware and transaction aware. They can be configured at runtime to provide numerous items of information. For example, latency of the transaction, minimum, maximum, average latency of the transactions, bandwidths, duration transaction, counting, and timing. These data are then used by analytics software executing on a dedicated CPU to determine issues with performance, safety, and security. Now the question is how we can assess and validate the proposed solution. As you know, it's close to impossible to test the automotive security solutions using the real vehicles due to the reasons such as it is difficult to perform the attacks on real environment due to specific road conditions required for testing, and obviously the safety reasons. Also, there are very limited number of driving scenarios that you can test using real vehicle on the real roads. Therefore, it is required to provide a replicate of the in-vehicle network to which we should have specific features to support automotive security testing scenarios, such as an industrial graded in-vehicle network. It should support realistic driving scenarios. It should also be able to support hardware plug and play support to test various number of ECUs. And finally, it should be used for the development and testing support for security solutions related to automotive industry. In this slide, you can see the diagram of the proposed automotive security testbed developed in Coventry University to assess and verify the Siemens hardware-based SoC monitoring solution. It consists of a car simulator, which is an open source car simulator called Carla to produce vehicle telemetry. The vehicle telemetry can be sent to a CAN simulator, which is a CAN software vector, to create a virtual CAN bus network, including number of virtual ECUs. Then this data can be translated to CAN messages, which is also be able to interface to the outside world through one of the ports of the computer. The data can be passed through various number of hardware components, such as the CAN filter, which act as a hacking device for one of the abuse cases, an OBD port, also other various physical ECUs, and finally to the data storage in order to access the data offline. And also at the end of the network, we can see the FPGA system accommodating the Siemens analytic IPs and also a number of virtual and emulated ECUs such as instrument cluster, door lock system, and an infotainment system. I should also mention that the Canoe is actually running on an RT rack, which is actually a real-time processor to ensure that the entire system is working close to real time. The emulated instrument cluster ECU is actually implemented in order to visualize the behavior of the other ECUs and also to notify the user in case of detection and mitigation of specific automotive threats. The other two emulated ECUs are actually related to the two abuse cases that we later want to test on the automotive testbed. One of them is a door lock system and the other one is the infotainment system. In this slide, you can see the actual testbed settings, which can be used to access and validate all automotive security solutions across the domain. In this section, I'm gonna talk through a number of examples of how the automotive testbed can be used to access and validate the proposed solution. A number of abuse cases related to both CAN bus and AXI bus vulnerabilities are selected. These abuse cases have been realized using the testbed to prove the capability of the Siemens solution to detect and mitigate the specific automotive threats. Here I'll briefly talk through three of them. In the first one, which is focused on the CAN bus, a mileage tampering attacks initiated by commercial CAN filter, which tampers with the odometer value to reduce the incremental rate of odometer. The hacking device supporting three filtration mode of 10, 20, and 30%. Here, the result table can clearly show the capability of analytic CPU to detect and correct the anomalies occurred in the CAN traffic related to the odometer values. I have to also mention that there is a machine learning algo which runs on top of one of the analytic CPUs in order to detect this type of anomalies. The next abuse case is focused on the malicious access to the AXI interconnect to compromise the infotainment system. In this scenario, an attacker has compromised the car infotainment system and malicious software is run on an infotainment system CPU. It tries to access system blocks or peripherals and memories that are present on the SoC interconnect and architecturally accessible to the CPU, but which should not be normally accessed by the CPU. Examples including memory areas, flash memory controllers, DRAM controllers, and CAN bus controllers. In fact, it can be any peripheral that the attacker could use to either maliciously trigger an action or obtain information from it. Inside the FPGA, the infotainment system is emulated by one of the ARM5 CPUs, which runs an application representing an infotainment software. You have to bear in mind that this application does not actually try to emulate the full functionality of the actual infotainment system, but rather it's capable of performing unexpected accesses to the AXI bus. It performs these accesses on request from the host Python session, which controls this FPGA execution. This request represents the attacker trying to maliciously access the forbidden AXI address. The analytic IP, which is called the CPU, which is one of the RISC-V CPUs, is responsible to, on the startup, is actually configuring the AXI bus monitor to inform the CPU when access is made by the infotainment CPU target, a forbidden AXI address range, and also during the normal operation, receives notifications sent from the bus monitor when it sees a forbidden access. To validate this emulated abuse case, a function is injected to the FPGA through the Python host session, which triggers an action emulating a malicious attack using the DMA mentioned above, which is also called AXI initiator. The AXI bus monitors can actually spot this access and blocks it, so it doesn't reach to the destination, which is another emulated ECU inside the FPGA. In addition to this, the CPU is notified about this malicious access and send a command to the emulated instrument cluster to visualize and notify the user by flashing a warning sign to report the user. Finally, the last abuse case is actually about the unauthorized car door lock unit tampering. In this scenario, the attacker gets access to an AXI bus initiator to perform an unauthorized car unlock. On the FPGA, an AXI bus sentry looks for access to the address range representing the car lock controller coming from a designated AXI bus initiator or a DMA emulating a compromised initiator. Similar to the previous scenario, on the startup, the CPU configures Siemens embedded analytics IP to monitor forbidden accesses from the DMA to the car lock controller. This time, the IP block used is not a bus monitor, but it's a bus sentry, which is unlike the bus monitors are capable of blocking AXI access in addition to monitoring them. Similar to the previous emulated abuse case, in order to validate this emulated abuse case, a function again injected to the FPGA through the Python host session, which triggers an action emulating a malicious attack using the DMA or AXI initiator. Using the AXI bus sentry, this malicious activity can be spotted and also blocked by the bus sentry. Again, similar to the previous abuse case, the CPU is notified about the malicious access and again send a command to the emulated instrument cluster to flash a warning sign and report the use to the user. So as a conclusion, we can say in this study, a novel on-chip silicon IP SiP customized for automotive safety and security application has been developed, and it has been implemented on a SoC FPGA, including bus filters, bus guardians, lock step monitors, and dedicated analytics IP, which is capable of detection and mitigation of SoC anomalies in real time, improving automotive SoCs highly secure and resilient to cyber attacks. It is capable of assessment by performing and integrating the SoC FPGA into a multi-components automotive testbed, by verifying it through 3 selected abuse cases. And finally, it illustrates the capability of the Siemens hardware solution to detect, block, and mitigate the cyber attacks in real time, showing promising of applying hardware-based monitoring solutions in automotive cyber security. Thank you.